Morning, everybody. I think we can start seeing the number of new people joining has tapered off. So now we get into process synthesis. And process synthesis, the first thing we need to do is to create a new process. So essentially the question I will ask you in process synthesis is design a process to make acetone, and and you've got to decide what are the steps that you're going to follow so that you can eventually land up with the process flow diagram that's going to make acetone. So obviously the first thing you'd need to look at is what am I going to make it out of, and therefore what reaction am I going to use to eventually land up with some acetone. And the next step, of course, then would be to see what excess there will be of stoichiometric and what we'll recycle, and eventually you'll do a mass balance, and you will do a mass balance around the recycle, and that is pretty much all that I'm going to require of you. That you need to pass a mass balance test that does the mass balance around the reaction and the recycle. So it may sound easy enough, but I find consistently that the fourth years have forgotten what they did in first year and find it difficult to do these mass balances. Right, so let's go on to the next slide. So the first thing when you're starting to develop a new process is you must find the physical property data so that you can properly figure out how you're going to model the process that you're designing. So you need to get thermophysical properties data, and Aspen has got an excellent database for that, but of course that's expensive. You've got DWSim, which is free. It's open source software, and it's got a fairly good, it has got a pretty good physical property database. So using DWSim, you let's have a look with it, what that notification was. If you've got DWSim, you've got a pretty good database, so you should be all right over there. Environmental and safety data, you need to look up what toxicity data, flammability data, so that you make sure. We'll talk about how to deal with toxic materials later. You need to know chemical prices. Many years ago, Chemical Marketing Reporter would quote, was a newspaper style publication that would quote bulk chemical prices. Nowadays it's more difficult to get real bulk chemical prices, and certainly you must be careful of using Merck prices. These specialty chemicals, they are usually analytical grade or something like that, and they will cost thousands of times more than the bulk chemicals that you'll be talking about. And ultimately, you may need experiments to check on crucial items, especially kinetics. You need to be sure that you don't that the journal articles that you've been using as the chemical kinetics, that they did their job properly and they measured correctly. No, Sigma Aldrich is the same as Merck. It's fine chemicals, and those ones you'll have way out prices. Look, it might give you an idea, because if you look at sodium bicarbonate or something like that, you may find that Sigma Aldrich will charge you 100 Rand a kilogram, and then you can go to Pick and Pay and buy that for 20 Rand a kilogram. Prices vary so much at these specialty chemical places. But if you search deep enough, you do find these bulk chemical prices. Right, synthesis, preliminary process synthesis. Synthesis involves selection of the processing mode, whether it's continuous or batch. And of course, we will normally be considering just the continuous processes, and the batch processes are when you're producing fine chemicals or specialty chemicals. And all of your training has essentially been in how to design continuous processes. Fixing the chemical state of raw materials, products, byproducts, noting the differences between them. So physical state, we'll talk about a little bit later, exactly what that means, but that is just the physical properties of that material that's going into your process. Temperature, pressure, all these sort of things. Is it liquid? Is it gas? Is it solid? Process operations. We need to decide which process operations, which unit operations we need. Those are the flow sheet building blocks. And now we come to these synthesis steps, 5 synthesis steps. So this section, process creation, is defined by these 5 synthesis steps. And now these 5 synthesis steps are really horrible. The way they're written in the textbook: eliminate differences in molecular types. What that means is, if you're starting with sodium carbonate and you want to make sodium bicarbonate, those are 2 different. You're trying to make sodium bicarbonate, and you're starting with something that is a different molecular type, and you need to react something with it so that you can make the correct molecular type. So it's a rather obtuse way of saying do chemical reactions. So step number 1, do chemical reaction and decide which chemical reaction you're going to use. Next, distribute the chemicals by matching sources and sinks. And that is what we can translate as decide what you want to recycle. Because if you have an excess of one chemical, then you don't want to throw that away because it is a reactant. So therefore, you will rather recycle it back to the start, so that you don't throw any of your resources away. Eventually, eliminate differences in composition. So after the reactor, you've got a mixture of different chemicals, including the one that you want. So that composition of that stream is wrong, and you need to fix that. And how do you fix that? You do separation. So even step number 3, eliminate differences in composition, has gotten very easy explanation. Separation. Do your separation. Finally, fourthly, eliminate differences in temperature, pressure, and phase. So as you're going through a chemical process, you would need a different temperature. The reaction will proceed only at certain temperatures, or the catalyst that you're using will only operate at various temperatures and pressures, and it'll operate in the gas phase or the liquid phase or both. You need to essentially decide what pressures, temperatures, and phases you need, and then you need to actually change those temperatures, pressures, and phases. So you need to put in a pump. If you need a change of pressure, you can put in a pump, or if it's a vapor, you would need to put in a compressor. And this is something that many students get wrong in the final exam. Recognizing, is it a liquid, is it a solid? Is it a liquid, is it a vapor? And whether you should put in a pump or a compressor. And those have got different symbols as in process flow diagrams. So that one's important. Temperature, what you're going to use, heat exchanger, and eventually phase. You might change your phase as well if you need to actually change. A feed material comes in as a liquid, but it must operate in the reactor as a vapor. You would want to boil it off first, because otherwise you can't boil it off in the reaction vessel. Otherwise, the temperature would be wrong. Now let me get back to comments. Compressor is for gas and a pump is for liquids, correct? All right, so this thing about eliminating differences in temperature, pressure, and phase, that you just put into a block, and you don't, if you are changing phase, you put that into a single block. And then if you superheat, you're changing phase from liquid to gas, for instance, you put in the change of phase in a single block, and then if you need to superheat the vapor, then you put that into a separate block where it is the change in temperature. So you're starting with a vapor at its bubble point, at its dew point, and you superheating it to the temperature of the reactor, for instance. Which equipment is that you're talking about, Yuri? Would you ever use such equipment on supercritical fluids? Oh, the pumps or compressors? No, you wouldn't. It's quite interesting. When you compress with isentropic compression, the temperature always goes up. And so if you start with a vapor at its dew point, the temperature goes up more than the boiling point goes up, because you're increasing the pressure. So in other words, if you put in a vapor at its dew point into the front of a compressor, and it compresses to a higher pressure, it never forms, or I've never come across it where it actually forms a liquid as it's going up in temperature. So if you are working with a supercritical fluid, you would compress the gas. Let's say you want to use supercritical CO2, and depending on and let's say you're getting CO2 at a low pressure, you would use a compressor then to compress that to above the supercritical pressure, which would be 80 bar or so, and then you'd cool it down to below 30 bar, which is the critical temperature, and then that will be, or you'd cool it down to exactly the critical temperature, which is about 30 degrees C, and then you'll have your supercritical fluid. All right. So yeah, integrate tasks is where you combine these tasks into unit operations. So in some cases, let's say you're putting this liquid into a reactor, you would probably want to still change the phase to the reactor to a gas if the reactor is operating in the gas phase, but you don't necessarily need to increase the temperature. You don't need to superheat it in the reactor. The reactor might be exothermic, and therefore you can integrate that task of superheating into the reactor itself. So integrating tasks is simply the task of going from changes in temperature, pressure, and phase, and integrating them into unit operations, which might be able to do several of these tasks in a single unit operation. A kettle reboiler, for instance, can change the phase and it can change the temperature. You can put in a cold stream into a kettle reboiler and change the phase to a vapor phase, even though you have to preheat it. It can be preheated in the same unit operation. So that's what integrated tasks is all about. Right, the chemical state, I said we'll talk about this a little bit later. Decide on the raw material and the product specification. So you want to know what is the flow rate of that raw material, its composition. So each of the chemical species that you've got in that stream, the phase, the form, and that is particle size distribution usually. And particle shape is also important. So all of these things become important when you process a stream that's going in. If it is a solid stream, then particle size distribution is important, and the particle shape is important. And that you do in CPA, which you'll be doing simultaneously with this course. Then you need to look at what its temperature is and what its pressure is, and that now you've defined the chemical state of that pipe that's coming in with the raw material, of the stream that's within the pipe that's coming in as your raw material. Okay. All right, so this is what I was talking about. Those 5 steps, which we call the synthesis steps, is actually very much easier translated into, number 1, figure out which chemical reaction you're going to use. Distribute the chemicals. Here it says mixing, mixing and recycling. So the recycle is important here. Separation. This is now to get you want to land up with a pure material that you're looking for, the pure product that you're looking for. And so you would need to separate out the other things, and some of them you would recycle. Then there's temperature, pressure, and phase change, which you put into separate blocks, eliminating differences in temperature, pressure, and phase, and ultimately integrate tasks, and that means you're drawing your process flow diagram. Right, so we're going to do an example, and this is the best way to illustrate these 5 steps that you need to follow. In the tests and exams, essentially I ask those 5 steps as different questions. It might be the same unit, the same process that you're developing, but I will ask them as 5 different questions. Maybe question 1, A, B, C, D, E will be those 5 steps that you do. Okay, so let's look at vinyl chloride manufacture as our example. Right, so the first thing is the database. We need to figure out what we can use as raw materials, what their physical properties are. So we write up this formula, molecular weight, the molecular weight of the materials, the acetylene and chlorine, dichloroethane, ethylene, hydrogen chloride, vinyl chloride are all materials we could be using, and chemical formula, chemical structure, so we understand what we're talking about. So have a look at these things. We've got dichloroethane is interesting. It's got no double bonds in it. Ethylene, of course, we know it's got the double bond, but this is what we're looking for. So two carbons and 1 chlorine. So you can compare that with this one, which has got the single bond. Dichloroethane has got the single bond, and therefore it's got 3 molecules attached to it, the 2 hydrogens and a chlorine. Here we've got 2 molecules attached. There's carbon, and only one of them is chlorine. Okay, so let's go on to the next slide. So now we look at the different ways, the different reaction paths we can use to get to our vinyl chloride monomer. So there is our vinyl chloride monomer, C2H3 Cl. We can do it with direct chlorination of ethylene. Ethylene plus chlorine gas gives vinyl chloride monomer plus hydrochloric acid. It's not hydrochloric acid, that's actually hydrogen chloride because it's not in water. Advantages: it's an attractive solution for the specific problem that I entered as alternative to in the analysis of the primitive problem. Let me just explain what we're talking about in the primitive problem, and that is if I say you must design a process that can produce 100,000 tons of vinyl chloride monomer at 99% purity. That is the definition of the primitive problem. So this is what I give you in the exam. That very simple. Just a single line says 100,000 tons per annum vinyl chloride monomer at 99% purity. And then you've got to figure out all of the steps yourself and eventually land up at a process flow diagram. That is what process synthesis is about. So this one, it's a nice easy reaction. It occurs spontaneously at a few hundred degrees C. The disadvantage is it doesn't give a high yield of vinyl chloride without simultaneously producing large amounts of byproducts such as dichloroethylene. Now that's a double bonded dichloro. Half of the expense of chlorine. Of course, chlorine gas is expensive. Well, I think in most of the world, it's created by electrolytically breaking sodium chloride, and the electricity is expensive. It's addition of a lot of gas, and the materials of construction of such a thing is really expensive. Half of the expense of chlorine is consumed to produce hydrogen chloride byproduct, which may not be sold easily. So it's not that many places that will value hydrogen chloride. And if you actually need to get rid of it, it's not an environmentally friendly thing to get rid of. Let's move on. Hydrochlorination of acetylene. So acetylene is an interesting thing. It's a very high energy type of molecule, and because it's a high energy type of molecule, it gives free energy with a low energy molecule like hydrogen chloride, makes it a viable reaction and goes immediately to a vinyl chloride monomer, which is exactly what you want. So really neat. The advantages: it provides a good conversion of acetylene, 98% conversion. Vinyl chloride in the presence of a mercury catalyst impregnated in activated carbon at atmospheric pressure. So really simple, and these are fairly moderate reaction conditions, hence this reaction deserves further study. But the disadvantages are the flammability limits of acetylene. Now this is really unusual. 2.5 is fine. It's low. Flammability limits are typically around 4% in air. But this is unusual, going up to 100%. So in other words, you can detonate acetylene, pure acetylene. You don't even need oxygen, and the reason is acetylene makes a hydrocarbon. So you can detonate it by making you can make diesel in a single step. The reaction occurs very fast because it's exothermic, and therefore it's autocatalytic. As it gets exothermic, it makes everything hot, and then it happily goes into a long chain hydrocarbon. And that's the reason that when you get an acetylene bottle from Afrox, it is actually acetylene that's dissolved in acetone. I think it's acetone, but they actually dissolve it there so that you keep the acetylene molecules apart from each other. So it's strange stuff. Not many things will be able to react with themselves. So yeah, it's stuff that you don't want to deal with regularly. Going back to acetylene, this is the reason you've got when you're working using acetylene to cut metal, an acetylene cutting torch. The acetylene line has got a flashback arrestor, so that if the flame goes back into the acetylene line, even without oxygen, it can propagate backwards in the acetylene line into the gas cylinder. So they've got these flashback arrestors in acetylene torches. Okay, so thermal cracking of dichloroethane from the chlorination. So first of all, we make dichloroethane. We chlorinate ethylene. There we go. And then we make dichloroethane. And the dichloroethane we further react to make the vinyl chloride monomer plus hydrogen chloride. And if you add these two together there, we can eliminate the intermediate, the dichloroethane, and essentially it works out that you are making the first reaction that we actually said. It's just a different reaction mechanism that we're talking of, or there is an intermediate going this route. So the advantages is going to dichloroethane is an exothermic reaction, and it gives you 98% conversion at 90 degrees C and 1 atmosphere with a Friedel-Crafts catalyst such as ferric chloride. This intermediate is converted to vinyl chloride by thermal cracking according to an endothermic reaction 2.4, which occurs spontaneously at 500 degrees C with conversions as high as 65%. As high as, okay, so it's not great conversion, but 65% we can live with, because if we don't react all of the dichloroethane, it is a relatively easy compound to, it's a liquid at room temperature, so it's an easy compound to store and to recycle. The disadvantage, half of the expensive chlorine is consumed of the actual chlorine molecule. One of them is going to your product, one of them is going to HCl, which is not a particularly valuable product. Right, so that was number 3. So it is essentially, overall, it's the same as the first option we looked at, which is this reaction over there. The second option we looked at was acetylene. This is the third one. And now we'll go on to the fourth. Thermal cracking of dichloroethane from oxychlorination of ethylene. So here we take ethylene, 2 hydrogen chlorides plus some oxygen. And there we can make water. So we make dichloroethane and water, and then with that dichloroethane reaction we were talking about, we can make vinyl chloride monomer and HCl. Put them together, it's ethylene, HCl, and now we're using HCl plus oxygen, also a cheap, easily available material, resource, and we make vinyl chloride monomer and water. And water is easier to get rid of if it has a low value, because it is environmentally okay to get rid of water. So Deerwald has asked a question: is the different reaction and pros and cons what one obtains typically from literature and experimental data? Yeah, that is correct. You've hit the nail on the head there, because I seldom ask this part. choosing your chemical reaction, I seldom ask that in the exams and tests, because I would then have to give you all of this information about the catalysts and the conversions and things like that. So yeah, but in your design project, you're gonna have to go through this step yourself. You'll have to look at what is possible, what people have done, what are the conversions, and what you're going to choose for your design project. Okay. Yeah, so let's have a look at the advantages. It's a highly exothermic reaction, achieves 95% conversion to dichloroethane in the presence of a copper catalyst, followed by a pyrolysis step, which is the normal one in reaction path 3. And it's an excellent candidate when the cost of HCl is low, because you can use up HCl. It's an inexpensive raw material there. And it's a solution for the specific problem donated as alternative 3. The disadvantages: economics dependent on the cost of HCl. So yes, it's only when HCl is an inexpensive material. And now we go on to the last one. A balanced process for the chlorination of ethylene. So there we go. The first one we dealt with, make ethylene and chlorine makes dichloroethane, right? Ethylene and chlorine makes dichloroethane. Ethylene plus HCl. So that's also the oxygenation thing to make dichloroethane. And water, and now you've got two dichloroethanes, and you can make two vinyl chloride monomers plus two HCl, and you can see the HCl's cancel out. There's two HCl's and there's two HCl's on the left hand side. So this looks rather nice. Two ethylenes plus chlorine gas plus oxygen, and you get your vinyl chloride monomer and water. So it's advantages, all looks like advantages. No, yeah, I think classically because it's an intermediate, it's not even an intermediate. Yeah, it depends on, if you do all of these in the same reactor, then you would consider it as a catalyst. But if you don't do it in the same reactor, then it's not really, yeah, it just takes part in the reaction. Overall, because you don't use it up or create it, you can consider it that, but when it happens in different reactions or at different places in the reactor, you don't consider it a catalyst. Okay, so all chlorine is converted to vinyl chloride monomer, so which is pretty good, and there are no byproducts because water is not really considered a byproduct. So you don't have to go and sell something. Okay, let's move on from there. Right, so now we've got those 5 reaction paths that are possible. So now, the first thing we do, we look at reaction path 1, and we eliminate it due to its low selectivity. So compared to the other paths, reaction path 1 was just, it just it didn't compare well to the others, so we simply eliminate that. What we are trying to do is to find which is the best of those alternative pathways. So that leaves 4 alternative paths, and what we're going to do next is just have a look at the gross profit. In other words, how much does it cost for the raw materials, and how much money can we get for the products that we make. So we go and look up in the old days Chemical Marketing Reporter, and we've got it in cents per pound because that's what the textbook uses. And water doesn't have value. Oxygen doesn't cost much. It's a really interesting molecule because it's got a high energy value because you use it when you react it. It is the thing that creates an exothermic reaction when you react it with a hydrocarbon. It's not so much that the energy is in the hydrocarbon. The energy is in the energy is in the oxygen itself, and it costs, in relative terms, bulk prices, liquid oxygen is relatively inexpensive. Okay, they've made it 0, but never mind that. In cents per pound, it might be 0, something. Okay, so we've got the chemical prices, and then what do we find? We have a look at the cost of using acetylene, which is really expensive. Let's just go back quickly and have a look at acetylene. We look down the prices. There's acetylene at 50, much more expensive, more than double even the closest, even more than double your actual product that you're trying to make. So, so when we have a look at using acetylene and HCl, we find that we would actually make a loss. Never mind the cost of building the plant, never mind the cost of operating the plant. Simply, we are making something that is less valuable than the stuff we're putting in, and that's the main reason why one would do this gross profit calculation, is simply to eliminate losers. So this one's just not at all viable. And then you can see that these two are a long way behind the profitability of this reaction. So it gives you a really good indication that this reaction was easy enough to do. It was a 2-step process. You made the vinyl, you made the dichloroethane, and then you had that pyrolysis reaction at 65% conversion. And those are all viable chemical reactions, relatively easy to do, and it tends to give you the highest gross profit. And this is 12 versus 7.5, and that's quite a big difference. So therefore, we're gonna choose reaction 3 as our most viable way of making this vinyl chloride monomer. Okay, so that's the whole process about choosing the chemical reaction. And now we know how exactly we're going to make it. So this is the preliminary flow sheet for path 3. So we've got the direct chlorination, chlorine plus ethylene, and we make dichloroethane. There's the dichloroethane. There's the reaction, and then we use that dichloroethane pyrolysis at 500 degrees C, and that will make, with 65% conversion, it's going to make vinyl chloride monomer and HCl. And because it's 65% conversion, there is going to be some unreacted dichloroethane over there. Yes, Alexander, we would have to consider the energy costs, especially because of the pyrolysis. But you'll find that the cost of energy is going to be relatively low compared to that much bigger gross profit. So yeah, you take a call on this one. That with such a big difference in the gross profit that you would expect, again, this is with experience, you'll expect the cost of energy would be much lower. So what we need is some fuel here But the cost of normal fuel, which might be natural gas, or it might be heavy fuel oil, the cost of energy to drive that pyrolysis is relatively small compared to that gross profit. Yes, you do take into account the possibility of selling the products. Let's just go back to that gross profit. So yeah, you look at, for instance, here's the reaction path 3, and we know that the hydrogen chloride is 18 cents per pound. So you do take that into account. We know the molecular weight. We know how many pounds. If you're starting with this number of pounds of each of these things, stoichiometric, then you'll make 36 pounds, and therefore you'd make for 1 pound of vinyl chloride monomer, you're going to make 0.58, and therefore you could work out the gross profit. So there, 22 times 1. So that is the positive that you're going to make. You're going to be able to sell the vinyl chloride monomer. So that's 22 times 1 plus 18 times 0.58. And then the rest of the stuff will be the raw materials. So it's minus 18 times 0.449 plus minus 11 times 1.134. And that's how we got the 11.94. And that's the same as all of these gross profits. You would take into account all of the values of all of your materials, including byproducts you make. Okay. So now we would see, if you take this process straight, you'll see that we are going to make HCl, and we are going to make vinyl chloride monomer. And overall, the dichloroethane, we're not going to show coming out because we would simply recycle it, because we can use it for the pyrolysis. That is what goes into the pyrolysis. So this would simply recycle. And if you look overall, one mole of chlorine would react with 1 mole of ethylene and make 1 mole of HCl, 1 mole of that. Let me just check the stoichiometry, but I think that is it. There we go, pound moles. 1 mole of that plus 1 mole of that gives 1 mole plus 1 mole. And then you work that out into kilograms. We would work it out into kilograms. And that will give you your masses. So you ignore that dichloroethane, because you're not going to chuck away something that is valuable, something that you are going to use in your reaction. If you are going to recycle all of the dichloroethane, you would not want to put in excess ethylene into the process as a whole. You would always be putting in a stoichiometric amount, because if you put in excess ethylene, that ethylene would have to come out at the back of the reactor, and it is a valuable raw material that you're using. So always stoichiometric amounts coming in, stoichiometric amounts coming out, unless there is reason that you don't have that. So there might be reasons stated in the original problem that you don't have it stoichiometric, but generally that is the thing. And this is where students go wrong on the mass balance, usually not realizing that it has to be stoichiometric, because they get confused with all of the recycles and things that we're going to do next. And first look at the overall, the big picture. That this envelope that we're talking about over here, and see what you need to go. If you want to make 100,000 pounds per hour of vinyl chloride monomer, you could work out just with stoichiometry how much of these raw materials you need, and therefore also how many pounds per hour of the byproduct you're going to make. Okay. Right, so now once we've got that overall mass balance, we can go on to doing the recycles. So now we say, right, we've got certain heat absorbed during the reaction. That's how much heat we've got to provide. This is at 500 degrees C. This one will be an exothermic reaction, but this exothermic reaction is not so valuable. You can't use this energy because it's at 90 degrees C and you need energy at 500 degrees C. So remember your thermo, that means that there is entropy being created as you go through this process. If you could use that if this was a higher temperature than that, if the exothermic reaction was a higher temperature than the endothermic reaction, you could use that energy and get it. Could use it to preheat. Yeah. You can still use that energy, and we'll get to that later when we combine units. So we're going to come to an end soon. I just want to go through to the recycle. So we're looking at the conditions, we're looking at the exothermicity, and now we're going to see what about that. This one is going out, but what about that? Obviously, we're going to take that dichloroethane and we're going to recycle it through to there. So there it's shown, and now you can work out exactly how much you would recycle. And really, the calculation you must do here is, I need to make how much must I make so that I can make my 1,000 pounds per hour of this vinyl chloride monomer? How much must I put in there, because I'm only getting 65% conversion? So you take the amount that the number of moles that you're making of this vinyl chloride monomer divided by the conversion, that divided by 0.65, and that gives you your total flow rate of dichloroethane that must go into the reactor. So it is, and that works out therefore as 105. Well, you know how many, 158 over there. Add 105,500 pounds per hour, you'll get what's 263,000 pounds per hour. Multiply that by 0.65, and you will get the right number of moles of vinyl chloride monomer that you get in your 100,000 pounds per hour. So that is the crux of the types of mass balance questions that I'm going to ask you in the tests and exams. All right, so we're going to leave it there. We'll carry on from this point. Remember, this is step number 2 in that 5-step process creation method, and we'll do the rest of those tomorrow. Okay, so let's shut off the recording. I'll take some questions.